Hi friends, dear friends. In the last part of the video, we discussed about the first quality property entitled as the lowering of vapor pressure. Dear friends, in that lecture, we particularly discussed about the vapor pressure and lowering of vapor pressure and how lowering of vapor pressure depends upon the concentration of solute or the mole fraction of solute, which is given by means of Raoult's law. So dear friends, today in this part of the video we will talk about the next qualitative property, which is entitled as the elevation of boiling point. So dear friends, first of all we should know what is the boiling point, and then we will move towards the elevation of boiling point. So boiling point is simply defined as the temperature at which vapor pressure vapor pressure of solvent becomes equal to the external pressure or atmospheric pressure or 1 atmosphere, or which is equal to 1.013 into 10 raised to 5 Newton per meter square. So this is very simple. The temperature at which vapor pressure of liquid becomes equal to the atmospheric pressure, that temperature is simply called as the boiling point. So it is also observed that when a non-electrolyte solute is dissolved in solvent, the vapor pressure of solvent is lowered or decreased, and hence the boiling point of so that solution or the solvent is raised or increased. Hence the conclusion is that the solution boils at always higher temperature, uh, higher temperature than that of pure solvent. So the boiling point of solution is always greater than that of the pure solvent. Suppose here, dear friends, here if we have the boiling point, we have the boiling point of solution is indicated by means of T, and that of pure solvent is T0, then the elevation in boiling point delta Te is indicated by T minus T0. So this is, it can be simply shown here. Now this graph indicates that the temperature, boiling temperature of solution indicated by means of T, and the boiling temperature of pure solvent indicated by means of T0, where P0 is the vapor pressure of pure solvent at temperature T0, and P is the vapor pressure of solution at temperature T0, while this P0 is the vapor pressure of solution at temperature T. So this is the graph that indicates the change in vapor pressure with the temperature. So by using the Clapeyron equation, the Clapeyron equation is simply ln of P2 upon P1, which is equal to latent heat of vaporization, or heat of vaporization delta HV. Here it is LV minus LV divided by R, and in the bracket simply 1 upon T2 minus 1 upon T1. So this is a simple case for in order to express the equation, and this equation is applicable to the curve where the temperatures are indicated by means of n, T and T0, and pressures P2 and P1 indicated by means of n, P and P0. So this is nothing but, suppose P0, that is nothing but the here P, suppose P is the higher pressure, corresponding temperature is T0, okay, and for this solution, and P0 is the temperature pressure P1 corresponding temperature T1 indicated by T. So this is after plotting by making the cross multiplication, it will be T minus T0, and this T minus T0 will become delta Te, and as it is a dilute solution, for the dilute solution the boiling points T and T0 are almost equal, means their difference is very negligible. That's why T minus T0 is equal to 0 or is nearly equal to 0. That's why T is nearly equal to T0. So this is very simple regarding with the elevation of boiling point. So here we will put this equation, these terms in this equation. Finally we are getting ln of P upon P0 minus is equal to minus LV. LV is the latent heat of vaporization per mole of the solvent divided by R in the bracket delta TE divided by T0 into T, and I already told you T is nearly equal to what? T0. That's why it will T0 into T becomes T0 square, and by putting this value in this equation we are getting ln of P upon P0 is equal to minus LV delta T divided by RT0. Dear friends, already we discussed about the Rolle's law in the previous part of the video, and the equation for the Rolle's law indicated by means of what? That is P upon P0 is equal to 1 minus x2. And this ln of 1 minus x2, or the P upon P0, or we can put this equation in this equation. If this is the case, then P upon P0 is simply replaced by means of 1 minus x2 is equal to minus LV delta TE divided by R into T0. So also we have the simplification of this, or the expansion of ln of 1 minus x2, that equal to minus x2 minus x2 square divided by 2 minus x2 cube divided by 3. And for dilute solution, this x2 is very small. This x2 mole fraction of solid is very small, and that's why the another terms of this, or the that is terms beyond minus x2 can be neglected, can be considered negligible. Therefore ln of 1 minus x2 is simply equal to minus x2, and if we'll put this value here in this, then definitely we will get this, that instead of this ln of 1 minus x2 there will be minus x2, minus becomes plus. That's why we are getting x2 is equal to LV delta T divided by RT0 square, and that's why we can write this equation for what? Delta TE means the elevation of boiling point is equal to RT0 square divided by LV into x2. So from this equation we can conclude this elevation of boiling point means delta TE is directly proportional to the mole fraction of solute x2. It's very simple regarding with this. So this is the conclusion. But this x2 is what? This x2 is the mole fraction of solute, and it can be written in terms of number of moles of solute and the solvent, that is simply x2 is equal to n2 upon n1 plus n2. And but for dilute solution, the n1 is very greater than n2, therefore the addition of n2 plus n1 can be written as only n1. That's why we are getting x2 is equal to n2 upon n1. So this is simply equation that we are getting, and if we put this in this equation, then simply we are getting this delta T is equal to RT0 square into L divided by LV into n2 upon n1. This n means the number of moles of solute and solvent can be expressed in terms of weight and the molecular weight of solute and the solvent. That number of moles is always the ratio of molecular weight divided by, it is the ratio of weight divided by molecular weight. For n1 it will be W1 upon m1, and for n2 it will be simply W2 divided by n2. So here this is, if we put these values of n1 and n2 in this above equation, simply we are getting this equation, that delta TE is equal to RT0 square divided by LV into W2 upon m2 into m1 divided by W1. So finally, this latent heat of vaporization per mole, latent heat of vaporization per mole of substance is the multiplication of heat of vaporization into molecular weight of solvent. So this LV can be replaced here, can be replaced here by means of the multiplication of LV into M1. So simply we are getting these terms here, and by simplification of all these terms, so this m1 and this m1 will get cancelled, and simply we will have the delta T is equal to RT0 square divided by LV into W2 divided by M2 into W1. So for the solution containing N2 mole of solute in W1 gram of solvent, the molality is indicated by means of, and simply this m, small m, that one that is 1000 into W2 divided by m2 into W1. And if we will rearrange this equation by dividing and multiplying by 1000, we will get this equation, that is delta TE is equal to RT0 square upon 1000 into LV into 1000 divided and multiplied by 1000 into W2 divided by M2 into W1. Dear friend, this term is the value of what? M. That's why we are getting this equation, delta T is equal to RT0 square divided by 1000 into LV into small m. That's why for the given solvent we will simply consider some constant LV and T0. These are the constant because T0 is the boiling point of pure solvent that always remains constant. R is the Rydberg constant, that is also the constant. LV, heat of vaporization per gram of substance, is also constant for the solvent. That's why all this term RT0 divided by 1000 into LV, these all terms are constant, and instead of this constant we will take the new constant indicated by Kb, and that's why we are getting the equation delta Te into delta Te is equal to Kb into small m. So where Kb is given by RT0 square upon 1000 into LV. If we are interested to determine the value of Kb, then we will put the values of all these constant R, T0 and LV. So this is 2.25289 and 373 for the water, 8.314. Then we are getting Kb is equal to 0.512 Kelvin kg per mole. This is very simple. Dear friends, based upon the same, we have one numerical, because the main purpose or the application of colligative property is to determine the molecular weight of unknown solute. So here there is a one numerical based upon the same that calculate the molecular weight of urea if a solution containing 2 gram of urea in 81.3 gram of water boils at 373.21 Kelvin temperature, and the Kb for water is given, that is 0.512 Kelvin kg per mole, and the boiling point of water is also provided 373. So this is the boiling point of water, that is 377. So dear friends, this is the value of what? T0, because this is the boiling point of pure solvent. 373.21, this is the value of what? This is the value of boiling point of solution indicated by T. 2 gram of, there is solution of urea in water, means 2 gram, it is the value of weight of solute W2, and 81.3, this is the weight of solvent, means it is the value of W1. So all these things are provided, and this is the Kb, 0.512 Kelvin kg per mole, and if we have the formula for molecular weight of solute is M2 is equal to 1000 into Kb into W2 divided by W1 into delta Te. Delta T means the 373.21 minus 373, that becomes what? 0.81. By calculating all this, we got this equation: molecular weight of solute 59.98 gram per mole. So this is all about elevation of boiling point, which is the second qualitative property, and it also depends upon the concentration of solute that we discussed, that from the equation delta T is equal to Kb into molality of the solution. It means that this elevation of boiling point also depends upon the relative number of solute and the solvent molecules present in the solution. So dear friends, in this way we will resume in the next part of the video to discuss the next qualitative property, which is entitled as the depression of freezing point. Thank you very much.